Okay, so our last section we're going to look at in Chapter 2 is 2.5. Similar to what we did yesterday, except we're going to be solving inequalities that have higher powers. Okay, so instead of them just being linear, we're going to look at quadratic, and maybe one cubic, but you'll see when we get to it. It's not too bad. All right, so I think we've seen this formula before. Okay, that's the formula for projectile motion. And what we did is, before we answered questions saying, when will an object be, say, exactly at 50 feet? Well, now we can ask a question and change this to an inequality. We can say, when will an object be at least 50 feet high? Okay, so that's greater than or equal to 50 feet. Or we could switch it and say, when will an object be below a certain value? Okay, when will it be less than or equal? Okay, so when I had this formula before, I used exactly the same variables, and each variable means the same thing. S is your height, t is your time. V sub 0 is an initial velocity that the object is thrown or released at. And S sub 0 is an initial height off the ground. If they say an object is released from ground level, then that would mean the initial height would be 0. Okay, and in a lot of problems, we talk about ground level. Not every problem, but quite a few. All right, so in this problem, we're going to throw a ball straight up from ground level with an initial velocity of 80 feet per second. Okay, does everybody have the projectile motion equation? Okay. So I want to know when the ball will be at least 64 feet off the ground. Yeah, I don't necessarily want to know when it's exactly 64 feet. I want to know when it's 64 feet or higher or greater. Okay, so if I go back to my formula, what letter in my formula represents height? S. So I basically want to know this. When is the height greater than or equal to 64? The only thing I have to figure out is, how do I represent my height? Well, that's where the formula comes in. Okay, so I'm going to write the formula for the height of this object. And then I'll plug it in right there. Okay. Can somebody remind me, how does the formula start?
16t squared, right? Or negative 16t squared.
Yep, negative 16t squared plus
v of o or
v sub 0, or yeah, that's how you say it. And what's my initial velocity here? 80. So I'm going to fill in 80 for the initial velocity, plus S sub 0, which is my initial height. What's my initial height in this problem? 0. Ground level. Okay, so now that's how I represent my height. I'm going to plug that into my formula and find out when is the height above or equal to 64 feet. Okay, so let's write that out, and then we'll solve it. Negative 16t squared plus 80t greater than or equal to 64. Now, there's two different ways we can do it. We can do it graphically, which I think is how I'm going to do it, or we could do it algebraically, and we're going to learn how to do it algebraically with what's called a sign pattern in a little bit. Okay, but let's just graph it. Put this in y1, put that in y2. All right, and let's see what it looks like. All right, so I've got negative 16 x squared plus 80. X, remember, you got to use x as your variable. You can't use t. and put 64 on the other side. All right, now we got to set our window. Okay, x or t in my formula represents time. What should be a minimum value for my time? 0. Time shouldn't be negative. The maximum amount of time, I don't know how long this object is in the air for. I'm going to guess it's in the air less than 8 seconds. If it's not, it's going to go off the screen, and I'll adjust it. Yep.
What was the second number?
64. Like 4.99999 seconds. When the time equals 5, then it's back on the ground. Okay, so sometimes you just have to think about it a little bit. Look at look at what you have. Try to use a little common sense. How do you multiply two things and get a positive? Right? List out your scenarios that could happen, and then usually one of them doesn't make sense because of different constraints in the problem, like time. Time is always a positive number. Okay. Any questions on that one? Okay, the next one is the same question we just did. I was going to go through it algebraically, but I'm going to hold off on part B because we're going to do enough algebraically when we do this. All right, so we're going to look at what's called a sign pattern. Okay, and by sign, I mean positive and negative. So we're going to look for where things are either positive or where things are negative. Okay, and we're going to start with this idea. Okay, every linear factor is 0 at exactly one value. All right, so what I mean is if you had something like this, that's a linear factor. There's exactly one number you could plug in for x, and it would make this 0. Okay, in this case, it's 3. 3 is the only number that you can plug in and get 0. How about this one? What number could you plug into this factor and it would make it 0? -8. So -8 is kind of the boundary between positives and negative results here. If you plug in -8, you get 0. If you plug in numbers bigger than -8, you're going to get positive answers. If you plug in numbers smaller than -8, you would get a negative answer. Okay, looking back at this one, 3. If you plug it in, you get 0. Plug in numbers larger than 3, like 5. Okay, numbers larger than 3 are going to give you positive results. Numbers smaller than 3 are going to give you negative results. That's pretty much all we have to do when we're looking for a sign pattern. Okay, find where the factor equals 0, and then determine, okay, if I plug in numbers bigger than that, what do I get? If I plug in numbers smaller than that, what do I get? Okay, here's another example of what I did up above. T minus 1 is exactly 0 if you plug in 1. And then I'm going to look at what happens if I plug in numbers bigger and smaller than that. Okay, and same thing here. T plus 4 is 0 when t is -4. And then we would look at what happens when you plug in numbers bigger and smaller than that. And the way we're going to look at it is we're going to make a number line. Okay, so we'll draw a number line like that. We're going to mark what number you plug in that makes it 0. So in this case, it's 1. So put a 1 on the number line. And what I did is I just broke the number line into two sections. Okay? I have a section to the left and a section to the right. I'm going to determine what kind of numbers do I get in each section if I plug them in. Okay? So if I plug in numbers 1, okay? If you want an example, think 5. Okay, that's a number bigger than 1. If I plug in a number bigger than 1, in for t, I will always get a positive result. If you give me a number smaller than 1 and plug it in right there for t, I will always get a negative result. Okay, so we're trying to figure out where we get positive and negative results. Okay, and you would have to do this for each factor. Okay, I did it for this one. I'm not going to do it for t plus 4 because we're going to do an example right now. Okay, and page 113 draws out exactly what I did. I like writing negative or positive, or if you want to use the symbols, you can do it that way. Negative, positive. All right, so we'll look at an example, and we're going to do everything up to this step. Okay, the last step is to combine our individual number lines into one number line and look at the final answer. Okay, but I'm not going to do this yet. I'll come back to these directions after we do the first part.
Could you go up for a minute?
Yep. All right. So if they ask us to solve a linear inequality, okay, the only method that you're going to have to use is what I just showed you, a sign pattern. The only problem with a sign pattern is it depends on being able to do this, factor. If you can't factor your problem, you can't use this method. Okay? In that case, we're going to have to go back and use the calculator. Okay? So as long as you can factor it, this method works. So hopefully this problem will factor. Okay. And what would be my first term in each parenthesis? Yeah, Denver?
X.
Okay, I'm going to need an x and a 2x. Okay, because 2x times x is 2x squared. Okay, what about my signs? Both positive, both negative, one of each. Yep.
2x minus x plus.
All right, we are going to need one of each, and it does matter which one you put where. I would do it exactly the way Ian said. Put the minus with the 2x, put the plus with the x. Now I need two numbers that multiply to give me 5. Jacob?
5 and 1.
5 and 1. And which one do you want to put in the first parenthesis? 5 or 1?
The 5.
Okay, we could try the 5, but I'll give you a hint, it won't work. So which one do you want to put?
So it'll be the 1.
Yeah, why don't we put the 1? So if we do it out, 2 times 5 gives me 10. Negative 1 times x is a negative 1. 10 take away 1, there's my 9x. If you had switched the numbers, you would just realize it doesn't work, and then you'd have to switch the numbers, and then it would work. All right, so I'm going to draw a number line for each of these factors. And I'm going to mark on the number line the number you plug in for x that makes them 0. All right. So when you have 2x minus 1, what would you plug in for x to make that first factor 0? Yeah, Lauren? Yeah, 1/2. Okay. If you're not sure, just off to the side, set this equal to 0 and solve it, and it comes out to 1/2. All right. What number would you plug into the second factor to make that 0? James?
Negative 5.
Negative 5. Okay, so now I've separated each number line into 2 sections, and now I'm going to examine what happens in each section. Okay, let's look at the first one. If I plug numbers bigger than 1/2, like 10, anything bigger than 1/2 in for x, will I get a positive answer or a negative answer? Well, Alex?
Positive.
Yeah. Just try plugging in a number bigger than 1/2. Try like 2. 2 times 2 is 4. 4 take away 1 is 3. That's positive. Okay. What's going to happen if I plug in numbers smaller than 1/2 for x? Okay, like 0. What kind of numbers would I get now?
Negative.
I would get a negative. And that's usually how it happens, unless they kind of switch it up and throw a negative in front like that, then it kind of reverses everything. But we don't have to worry about that in these problems. All right, let's try the second one. Right? What happens if I plug in numbers bigger than -5? What kind of answers would I get? I would get positives. And what if I plug in numbers smaller than -5 for x? I would get negative answers. Okay, so now we've got our number line for each individual factor. Now we're going to combine them together to look at the final answer. Okay, so now we're going to make one big number line, and I'm going to put both of those on it. -5 and 1/2. So now I've got 3 sections to look at. Okay, and remember what we're doing is we're multiplying. We're multiplying something times something, and we want to know where it's positive or greater than 0. Same thing. Okay, multiplying 2 things together, and we want to know where it's positive. So let's examine the behavior in each of the 3 sections. Let's look at numbers less than -5 in the first factor. What kind of numbers do I get if I plug in something less than -5 in the first factor? Yeah, I mean, I didn't mark -5, but it would be somewhere around there. So plug in numbers less than -5, I get a negative. And let's look at the second one. Less than -5 in the second one, another negative. And that means in this section, I would have negatives times negatives, which would be? This section would be positive. Okay, now we're going to look at numbers between -5 and 1/2. In the first factor, what kind of numbers do I get between -5 and 1/2? Yep, I get negatives. And between -5 and 1/2 in the second factor?
Positive.
Yep, I'm in the positive section. So that means in the middle, I have negatives times positives. So what's that middle section going to end up being? That's a negative. Now I'm going to look at numbers bigger than 1/2 in both. Okay, top one. Bigger than 1/2. What do I get? Positives. And in this one, bigger than 1/2? Positives again. So in the last section, I have positives times positives, which is a positive. Okay, now we can use that to answer the question. They want to know where this one is greater than 0. Okay, where is it positive? Here and here. So there's 2 sections where it's positive. Okay, in this left interval, that's from -infinity all the way up to -5. In this case, we do not include -5. Or, anyone think they can tell me the other interval where I'm positive? How would you write it? Alex?
Would that be 1/2 250?
Yep. That's your answer. Okay, and maybe you don't need to make all 3 sign charts the way I did, but I find if I skip making the 2 originals, people get confused with the final. So I'll do one more like this. Okay. So any questions on that? All right, it's a little different, but once you get used to it, it's not too hard. Okay, this is one that's a cubic. Okay, I told you we'd do 1 cubic, but I've already factored it for you. I would not give you a cubic and make you factor it. I definitely would give you a quadratic and make you factor, okay, but not a cubic. Okay, so it's already factored. So you're going to set up a number line for each factor. Okay, what value do you plug into the first factor to make it 0?
first one?
Yeah, the very first one.
0.
Yeah, 0. That one's pretty straightforward. What value do you plug into the second factor? -3. And the third factor? 1. And again, we're going to examine the behavior in each section. All right, first factor. Plug in numbers bigger than 0. What do you get? Positive. Less than 0? Negatives. Second factor. Plug in numbers larger than -3. What do you get? You get positive answers. And if you plug in less than -3, you get negative answers. Okay, last factor. We got our root at 1. That plug 1 in, you get 0. What if you plug in numbers bigger than 1? Positives. What if you plug in numbers smaller than 1? Negative. If you get confused, you could always just try one. Pick a number smaller than 1. 0. Plug it in for x and see what kind of answer you get. Now we're going to make a number line that combines all of that into 1. And how many sections are going to be on my final number line?
4.
Yeah, this one's going to have 4, right? Because we're going to have -3, 0, and 1. So my 4 sections are here, 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 and there. And what usually happens, I don't know if you guessed this or not, but the behavior always alternates positive, negative, or negative, positive. Okay, it always alternates in each section. So once you find the first one, you can really just assume the other ones. But we'll check the first 2, and then we'll assume the rest from there. All right, so off to the side, I'm going to check the behavior when I'm less than -3 in all of them, and I'm multiplying together. Okay, what kind of number do I get when I'm less than -3 in the first one?
Negative.
Okay, that's a negative. Less than -3 in the second one. That's another negative. And less than -3 in the third one. That's another negative. So in the first section, it's a negative times a negative times a negative, which is, that's a negative. Okay. Now let's check if we plug in a number between -3 and 0 in all of them. Okay, between -3 and 0 in the first one. That's in the negative section. Between -3 and 0 in the second one. That's a positive. And lastly, between -3 and 0 in the third one. That's a negative. So in the second section, you're going to have negatives times negatives, which is positive. Okay, and from here, if you want to check the other 2, you can, but this will be negative. This will be positive. Now go back up and look at the problem and ask, does it ask where it's above 0 or below 0? This one is above. Where is it greater than or equal to 0? Here and here. Now this time it says it can equal 0. Okay? So I'm going to include the endpoints from -3 to 0, or we can also go from 1 to infinity. Okay, so that's using a sign chart. Any questions on the sign chart? Okay. The only trick, well, 2 tricks, is you got to make sure you can factor it, and you have to make sure that you have 0 on one side. So if they started this problem like this, the first thing I would do is that. Move the 5 to the other side. Got to have 0, got to be able to factor. All right, so as I said, we're going to skip 2.6 and 2.7. I'm also going to skip this example. This would work out exactly the same. Whether you multiply negatives times negatives or divide them, it's the same rules. So do this problem just like you would do this problem. There's no difference between these two problems. Same answer. Okay, so we'll skip over that one. If you can't factor it, then that's when we use our graphing calculator. All right, so just to show you how it works, it's nothing you haven't really done before. Okay, type in one of them in y1. So x cubed minus 2x squared minus 5x plus 7. And I'm going to try to figure out where this graph is above or equal to this graph. So I'm going to try to figure out where blue is above red. Okay, so probably need to adjust my window a little bit. Well, I can kind of see it, but let's do zoom 6. Okay, so where is the blue above the red? All right. So anytime it crosses like a bunch of times like this, we got to look at it kind of carefully. Okay. Where is blue above red? Well, that's going to happen from here, okay, in this section that I'm trying to make look bolder, to there. And it's going to happen from here on forever. Okay, so there's two sections where the blue is above the red. Everywhere else it's below. All right, so what would I have to do 3 times? Yeah, I'd have to find the intercepts. So is everyone okay if I don't find them? Okay, let's just say this first intersection point is AB. This one is C comma D. And this one's E comma F. Okay, you'd have to go through and find all those intersects. And what does it say? Greater than or equal. So between A and C. Remember, when you write an interval, it's always x values. You never use y values. Okay. So between, looks like it's roughly -2 to, I don't know, a little bit past 1. Okay, but again, I'd have to find them, see what they come out to. So whatever A and C are, okay, between those two, or from what other value onto infinity. E. Okay, you'd have to find that using your intersect, but from E, which looks like it's about 3, maybe 3.5. Okay, from that value on, it'll be above. Okay, so that's how you do it if you can't use a sign chart. All right, so the last thing we'll look at, I don't think we're going to finish it today, but it's kind of an introduction to polynomials. And we've talked a little bit about polynomials and like what the highest exponent tells you, like how many turns it can take. That's what they mentioned in this section, okay, some of that stuff. So in general, you don't, I don't think you really need to write this part, but the idea of a polynomial is just you have something, it has a power, and then you write the next term, and usually it's a lower power, okay, like this, x to the 8th minus 2x to the 6th. You don't have to have every single exponent, but we usually just write them in decreasing order. Plus x squared minus 5. Okay, your last term usually doesn't even have a letter. It's just a constant. But the important thing with polynomials is these two facts. Your exponents have to be non-negative integers. When you have a polynomial, you cannot have decimals as exponents, and you can't have negatives as exponents. 0 is okay, but we usually, if it's a 0, we don't even write that term down. It would just be a constant, because anything to the 0 power is just a 1. Okay, so exponents can't be negative, can't be decimals, and the numbers in front, okay, or those numbers in front or the constant have to be real numbers. Okay, so you can have a fraction in front, that's fine. 2/3 x to the 8th, but what you can't have is fractions in the exponents. Okay, so no imaginary numbers anywhere in this whole thing. Okay, numbers that I circled have to be real. Okay, and as long as the first term doesn't have a coefficient of 0, then that first term is called your degree. Okay? If you did something like this, you just wiped the first term out. You put in a 0. So now it's not really the first term. It's not even there. Okay? That's now the first term. Okay? But as long as that first term doesn't have a coefficient of 0, that exponent, okay, whatever it happens to be, is called the degree of the polynomial. So the one I have up on the board, that would be called a degree 6 polynomial. Okay, and some polynomials have special names. If you have a degree 1, that's called linear. How about a degree 2? That one begins with a Q.
Quadratic.
That's a quadratic. And degree 3.
Cubic.
Yep, that's a cubic. And degree 4 we could call quartic, but in general, these are the only ones we give special names to. Okay, if you've got something higher than a degree 3, you just say it's a polynomial of degree 10. Okay, we don't have special names. Okay, the domain of a polynomial function is always all real numbers. Okay, that never changes. So the domain of a polynomial is always all real numbers. Because all you're doing in a polynomial is multiplying a number by another number or raising a number to a power. You can raise any number to any positive power you want. You'll never divide by 0, and you'll never take the square root of a negative. Okay? Those two things don't exist in polynomials. And those are the only two things that can mess up your domain. So domain is always all real numbers. The range depends. Okay, I can't say the range is always the same thing. It's not. Okay, but domain is always all real numbers. Okay, so these are what your cubic functions can look like. Okay, cubic functions can turn up to 2 times. And when I say up to, it doesn't mean they have to. They can, but they don't have to. Okay, so here's an example on the right of 2 cubic functions that do turn both times. And here's an example of a cubic on the left that starts to kind of turn, kind of flattens out a little, but then it just goes back up. Okay, your book has pictures on page 142. Of the cubics that I drew. So a 4th degree polynomial basically means your highest exponent is now a 4. And what that 4 does is it allows it to now take one more term. Okay? 4th degree polynomials can turn 3 times. Okay, so if something turns 3 times, you could get a shape like this. Okay, when you graph it, you could get a W shape. And page 143, he's got some more pictures of fourth degree polynomials. Okay, so what I'm just trying to get you to see here is kind of the connection between the highest exponent and how many turns the graph can take. It's always one less. Okay? That's 1 turn, 2 turns, 3 turns. Now, if I asked you how many times it could cross the x-axis, pretend that's your x-axis. It can cross up to 4 times. It could cross 3, okay, if it was just like that. It could cross 2, if you had it like that. And it could cross 1, if you had it just like that. It could also cross 0, if that was your x-axis. Okay? You like that?
That was me, that was better.
You said that's incredible.
Yeah. All right, so let me graph this one, and we'll just look at it and find the domain and range. Okay, so x to the 4th plus 5x cubed plus 2x squared minus 8x plus 1. Okay, for this, you could really just watch me do this. Well, don't think too hard about the domain. We talked about that earlier. What's the domain here? Yeah, it's all real numbers. You can take any number and raise it to the 4th power. You can cube any number you want. You can square any number and then double it. You can multiply any number by -8. You can do it. You can plug any number you want in for x. So domain is all reals. Okay, range. Well, let's look at my graph. How many times can this graph turn at most? It can cross the x-axis 4 times, but it could turn up to 3 times. And this one looks like it does do all the turns. I'm just going to set my y min a little lower. Let's try -20. Okay, so now the range is how high and low this graph goes. Does the graph go down forever? Nope, so then it has a minimum somewhere. Does the graph go up forever?
Yes.
Yes. So the graph does go up forever, to infinity and beyond. But it doesn't go down forever. So does anybody remember how you can find a minimum? It's the same menu we've used a lot.
Second calc,
Yep,
and then you go to minimum.
go to minimum. Okay. And to find a minimum, pick a point somewhere to the left, somewhere to the right, and do a guess. Okay. That's at -3.25, and we actually reached that value. Okay, so that describes all the values you're going to hit on the y-axis. -3.25 and up.
Wait, shouldn't the minimum be the y?
Oh, thank you. Yes, -11.95. Yes. Luke's exactly right, because domain is x. Range, you always want to write the y's. Lowest to highest. Yeah, thank you.
You're welcome, Hager. Not all of us are perfect.
Nope, definitely not me.
So, I mean, you're almost perfect.
Not quite. 5th degree polynomials, I'm not going to draw them. You can see them on page 153. They can take one more turn. So they could turn up to 4 times. Okay, but I think the last thing we'll look at is what's called a local min and a local max. Okay, what these are values that are lower or higher than everything else around them. Okay, I'm not saying that this is the lowest value ever that this function hits. In fact, it's not. This function goes down forever. But what I am saying is this value right here is lower than everything else around it. Okay, and same thing here. I'm not saying that this is the highest value that the function ever hits. But what I am saying is it's higher than everything around it. Okay? So a local maximum is a point on a graph that's higher than all other points around it, okay, over a certain interval. Okay, and a local minimum is a point on a graph that is lower than all other points around it. Okay. If you wanted to describe the absolute lowest point that the graph ever possibly hits, like in this one, that's called a global minimum. Okay, negative 11.95, that is the lowest y value this function ever hits. There is nothing lower. Okay, so that's a global minimum. That's a local minimum right here. It's not the lowest value ever, but it is the lowest value in this area. And this is a local maximum. It's not the highest value, but it is the highest value in that area. And together, the local mins and local maxes of a function are called local extrema. They're like the extreme values in a small area. Okay, so we'll finish up just by looking at this function, and we'll find the local minimum and the local maximum. It's exactly what we just did in this problem, really.
Mr. Hager,
Yeah.
can you just lower that?
Oh, yeah. All right, so let's type in x cubed minus 4x. Hit zoom 6. Okay, if a standard window doesn't work, I'll fix it, but that's perfect. And I'm going to start by finding my local min. Second, calc minimum. Pick a point left, pick a point right, and my guess. Okay, so there is my, that's the minimum. This is where it occurs. Okay, so the minimum is actually how low does it go? Okay, it goes to negative 3.07. But where does it hit that minimum? It's about 1.15. Okay, and same thing to do it as a max. Okay, second calc, maximum. Okay, and this one is it's kind of symmetrical. The min was at negative 3.07. The max is at positive 3.07. That doesn't always happen, so it's a good idea. Just check it. That's the max, and that's where it occurs. Okay. All right, so there's one thing left in 3.1, but we'll do that tomorrow when we start 3.2. So there's not that much left. On page 149, okay, I'm going to have you stop. 116, we did all of that. But page 149, I'm going to have you stop at, let's see. Don't have to do 25. We'll save that one for tomorrow. 29. We'll save that one for tomorrow. Actually, that's all we didn't cover. Okay. So just do those problems, except the one I put the line through. If you want to write them down and try them, you can. I'm going to assign them tomorrow. But if not, just worry about what's not crossed out.